In the last video, we talked about ring strain quite a bit, and I want to add to that with this one as we talk about conformations too. Now, cyclopropane, any 3 points in space always form a plane. So if I wanted to, I could draw this baby at kind of a perspective like this, and you could see it maybe closer to being 2D. But if I was to make it totally flat, so you can't even see the back side, like say you're looking at this bond here, you can't see this one back here from this perspective. It's not a line. This is my cyclopropane. And you would have a carbon here with a hydrogen that goes this way and a hydrogen that goes this way. Let's say that's this carbon here. And we might draw it this way here, like this. I hope you can see what I'm doing here. The back one, I'll put kind of right by it. Now, this isn't a double bond. This is the back side. I'm trying to draw this part of cyclopropane here. You're going to see this guy has a conformation where like hydrogen's somewhere like this, but so is this guy here. And that's these hydrogens here like this. They are somewhat too close together. This is not a very happy, campy situation. So it's not just that the bond angle is like loading up a spring here because these orbitals are bent. Here's one orbital. Here's another orbital. This angle that they form between them is not as great as a relaxed alkane. If I have butane, this angle is 109.5 degrees, and it leaves room for the orbital to overlap exactly end to end like this. And that's a nice straight line between these two bubbles. But that's not what is here on cyclopropane. It's a bent bond angle is what they call that, or a bent bond, excuse me. So not only do we have this torsional strain as a consequence, but these bent bonds mean that these electrons are too close to these electrons. They don't like it. They don't like it. And that means that the molecule itself is going to be a lot less stable. In fact, it might even be explosive under the right conditions. Let's look at another example. I always like cyclobutane because you can draw it as a square. I could just come in and say, here's my cyclobutane. But that's the two-dimensional world. If I'm to look at it in real perspective, it would be something like that. So yeah, you could draw it as a square if you're doing it flat 2D, but it doesn't really do a very good job depicting it. In fact, I think I'm going to open that a little wider so that we can draw it better like that. And we'll say that this part, I'm going to fill that. Can we fill it? Is it going to work? Yeah. So let's say that's coming out of the page. And here's a hydrogen, and here's a hydrogen, and there's a hydrogen, there's a hydro. And these guys will be off the page this way. So the beauty of cyclos, of course, is that they all have two hydrogens attached because they're all attached to two carbons in that way. One thing you might wonder is, like, why would these both be pointed up at the same time like this? What forces that kind of shape? You have a plane for these three, and then this guy's kind of bent up a ways like that. Why is that? Well, it actually creates more bond strain than if it was flat. If you imagine this being flat, this distance here is maximum. But this guy, if you were to look at it just from the top, is more like this. And this isn't here. So why did they want to get closer together if they don't like that? And it's because of the torsional strain with all these hydrogens. There's a real problem here. I'm going to pull out the Newman projection here. I want you to take a look at this because here's the other factor. Look at how the hydrogens line up on this. So if I'm looking at cyclobutane from one end here, what you see is that these hydrogens really do kind of get lined up on each other, which is really angering for them. That's not their favorite. Hydrogen would rather be off to the side this way and off to the side this way, away from everybody. But you can't determine that because this tetrahedral shape is mostly determined by these shared bonds. They're not like this, right? They are more like this, up kind of bumped out that way. So these hydrogens are forced to be somewhat in alignment. Now, if I bring that diagram back, this fourth carbon is kind of pushed up out of the plane for that reason. It's doing the best it can to compromise between the bond angles and between the hydrogen range. So you end up with this kind of strange angled shape, and every molecule will have different bond angles just a little bit as a consequence of behaviors like this. But what you want to be taking away from this is that there's a balance between the bond angle and the torsion caused by the hydrogens lining up in an unideal fashion. Now let's compare that with someone who's less angry. Let's look at cyclopentane for a second. So let's make a pentagon, like so. Now if I was to actually do cyclopentane, and I want to look at it as flat as I can, it would look more like this with kind of a bent up nose. Think of it as having a fold right there, kind of folded up. or at least that's how I think about it. Now the hydrogens, as they line up, aren't going to have as much steric or torsion, anger, steric, something else. We'll talk about that another time. The eclipsing on this, I have a diagram of this. If I'm to look at it like from this direction to these angles here, or if I want to try and look at it up from this direction here, you're going to get this diagram. And this Newman projection kind of shows you how well the hydrogens are lining up on this cyclopentane. And the one behind it, this one here, is not really lining up with the other hydrogen here. So let's say that that's this hydrogen and this hydrogen here facing a different direction. They're not as close together as they could be. If this was bent down, if it was laid flat, imagine like you push this carbon down, this angle would close up and you'd have these kind of aligned like that. And it might not seem like it matters because they're a whole bond length apart, but that's close enough to where these have an effective cloud that pushes on each other, right? So cyclopentane is able to form a much wider Newman projection spread, I guess we'd call it. Let's call it more staggered. That's what I'm looking for, a more staggered hydrogen arrangement or conformation. So cyclopentane is a lot more relaxed than cyclopropane or cyclobutane because these hydrogens, they're not so angry. They're able to kind of find their own free space out here like this. And this guy being bent up isn't going to really see the hydrogens down there. So not only is the bond angle close to the right one, you'd want 109 or whatever it is, 0.5. It's like, I can't even remember what it is, like 105 or something. It's just a little bit strained. And the hydrogens aren't totally staggered. If you look at this, they're not totally perfectly separated, but it's not bad either. So cyclopentane is a pretty low energy or low strain ring. It's pretty low strain. The perfect one is hexane. You won't have any ring strain. But this is a good example of one that's just really low torsion. Okay, last one. Let's look at the hero. Let's look at the real hero. Now we draw cyclohexane like this, but that's not three-dimensional. Real hexane looks kind of like this. And I'm going to thicken this up so that you can make it in your mind a little bit closer. And then it kind of is moving away from you like that. And maybe this is just a little bit thicker here. The in and out of the page kind of a thing. Doesn't matter. You get the idea. Now, it's really important to look at this and not see a hexagon anymore. I don't want you to see this and think that that's what cyclohexane looked like, because this is the one who forms these 109-degree bond angles. This is three-dimensional space, baby. If you're an observer and you go to look at the hydrogens on this, I'll try and draw them right. This one and then this one. So if I was to look at this, you should try to see that tetrahedron shape here like this, where if I draw that pyramid again, put your carbon in the middle, you see this tetrahedron here. Well, look at the two like this in here. That's this here. That's what these are here. That's your 109.5. So the other two being hydrogen, they're dang close to exactly what we would expect. Oops, let's keep the hydrogen there. So you're going to get 109.5 here, you're going to get 109 here, and they're on different axes, right? Different orientations. But it's all 109.5 degrees. They're as far apart as you could possibly hope for. So let's say I want to look like right up the pipe here, or right down the pipe this way. You want to line your scope up on the right along the bond here, which by the way is like a perfect end-on-end bond because they have the right bond angle, lets those orbitals line up just so perfectly. Well, what you're going to see, I have a picture of that too, is the ideal. You're going to get this guy here. Now that is looking at these two bonds right here from this angle. Notice something here. I'll use orange. Every single one of these hydrogens has a nice staggered conformation on the outside. So if I take these away and I want to draw these hydrogens here like this, if I was to look down this pipe, you'd have hydrogen, hydrogen, and then the two behind it you can't really see because this carbon's in the way, but one is popping up this way and one is popping out this way. Look at the angle between them. It's perfection. And the only reason that it doesn't take up the whole 3D space, of course, is because you got your carbons, right? You got to bond your carbons in some directions, but look, these hydrogens are as staggered as they can be, which means it's the lowest possible energy. Cyclohexane has absolutely no ring strain. So because of the angles that this molecule is able to form, the hydrogens are conformed, meaning like their arrangement is as far apart as possible, and the bond angles here are all a nice ideal 109.5 degrees, and that's exactly why cyclohexane is so common in nature. Of course, what you're really going to end up seeing are benzene rings because you're going to have double bonds in a lot of structures, and we'll talk about that at another time. But if you're just making cycloalkanes, well, cyclohexane is going to be your lowest energy conformation and the easiest one that you can produce because it's so naturally well formed. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.